Good morning, boys and girls. Mr. Murtara with you again here, and today we're going to talk about function operations, performing function operations. So just a few things here. We're going to, I know you've seen this before, but we are going to reintroduce function notation. Okay? Function notation is when we replace the y in a function, like with an f of x or a g of x. And the whole reason why we use f of x and g of x in function notation, or any other letter, like here you can see that we're using h of x's, f of x's, and g of x's. The whole reason we use function notation, or one of the main reasons we use function notation, is that further in math you go, you're going to start to deal with multiple functions. Instead of just having one function, you might have two or three that you're talking about. And so function notation, calling something f of x or g of x, allows us to differentiate between the functions. If these were both just y equals, there'd be no way, if I said, hey, look at that equation, you wouldn't know which one I'm talking about. But right now, if I say, hey, look at f of x, when I say f of x, I'm talking about the red equation right here. And we're talking about that one. Or if I said, hey, I want to talk about g of x, you know that g of x is talking about this equation right here. Okay? So function notation, one, allows us to talk about different equations separately. The other thing function notation allows us to do is, I can tell what I'm plugging in. If I say f of 1 equals 3, you know that I plugged a 1 in for the x value. The 1 is my input and the 3 is my output. It allows us to see that whole point. So these are some of the benefits of function notation. But today we're going to now get into operations with functions. Now when we say operations with functions, those operations that we are talking about are addition, subtraction, multiplication, and division. Okay, so basically today's going to be a lot of review. We are just going to go back to like our combining like terms, distributing, a lot of those type of things here. And we're just going to incorporate a lot of the, the polynomials and the functions that we have talked about in previous units. Okay, but bottom line is we're just going to name things differently. All right, so here we go. All right, let's start with addition. If I wanted you to find a new function h of x, and I get that by doing f of x plus g of x. The way we would find that is by doing h of x is equal to 3x, my f function, plus x plus 5, my g function. I'm just going to plug those functions in for, the ones where they're missing right here. F of x, g of x, g of x. I'm just going to plug those in. And this is where I'm saying it's all just going to be a lot of review because now I am just going to combine my like terms. Now really, I guess I could have put these in parentheses. And if I had put those, there's my f of x plus g of x. But if I had put those in parentheses, the first thing I would do is get rid of my parentheses by distributing the 1 in front. And I'm going to combine like terms. So 3x plus x is 4x. And then there is no constant. So h of x in this case would be 4x plus 5. And that is how I add functions. Okay, next let's talk subtraction. If I'm subtracting functions, same thing. I am just going to go ahead and, again, h of x is f of x, 3x, minus g of x, x plus 5. And I just need to combine my like terms. However, in this case, again, remember, when you distribute this negative, put a little 1 in front, and you need to distribute that negative to everything. So this becomes 3x minus x, which is 2x, and then negative 1 times 5, which is minus 5. So now h of x would be a different function. It would be 2x minus 5. Let's look at a little multiplication. Now with multiplying here, watch out. I notice this might just be a my computer thing, but it also might be on your notes, so just watch out. That should be a little dot indicating that we're multiplying these together. If your notes are like that and you see that little box, it just didn't come through from the printer. But hopefully yours has, f of x times g of x with a little dot meaning multiply. But now I just want to multiply my functions together. So in this case, because we're multiplying, again, pay attention to the sign of the operation that we're doing, I am going to distribute 3x. So 3x times x is 3x squared, and 3x times 5 is 15x. And here's why I'm saying this is just going to be, again, a lot of review. We have done all these adding, subtracting, multiplying before, all this dividing before. It's just using this new notation and getting comfortable with our new notation. All right, and now last but not least, division. All right, so when I divide h of x equals f of x, 3x, over g of x, x plus 5, here's the good news. I don't actually need to go and divide this into our long and synthetic division, We just want to make sure it's simplified. So going back to the first unit we did coming back from break, with our rational expressions, you want to try to factor. And again, if you can't factor, then you can't kill. In this case, I cannot factor anything out. So this is just going to be 3x over x plus 5. And that is my answer. Okay, next now, when we talk about the domain, remember the domain is the inputs or the x's, right? The x values that we could have. When we talk about the domain of these new functions that we were creating from two old functions, okay? The domain, you want to know, consists of the x values that are in the domains of both f of x and g of x. And just what we mean by this is that if the domain is restricted in f or g, then the domain would also have to be restricted in this composite function, okay? And so this will make a little more sense as we kind of move on and we play with some of these functions down below. But the way I kind of view it is these are like the parent functions. So if something's going on with a parent, then it's also going to go on with the kids, okay? With the function they've created together, all right? So again, in this case, if we look at the functions up above here, well, let me talk about this first. There's only two places so far that we have had restricted domains, okay? If you think about it in all the functions we've talked about. One of those places we've had restricted domains is inside of a square root. If x is inside of a square root, then x cannot be negative, right? We cannot take the square root of a negative number. So that is one place we have had restricted domains. And then the other place we've had restricted domains is when the denominator equals 0, right? Like we talked about how if x is on the bottom of a fraction, or if you have x on the bottom of a fraction, the bottom of a fraction can't equal 0. And that's how we had things like holes created and vertical asymptotes. So these are the two things that you need to watch out for. If you see a square root in your function, or if you see a fraction, you got to watch out for those two things because those are going to put restrictions on your domain. So going back to up here for our addition, my answer is 4x plus 5, no square roots, no fractions. And if I look at the parent functions, no square roots, no fractions. So my domain would be all real numbers. There it is. Same thing for the subtraction one. Again, no square roots, no fractions, so I don't have to worry. No square roots, no fractions in our parent functions. We already talked about that. So again, the domain would be all real numbers. And this would also be true for the multiplication. Hey, the domain, no square roots, no fractions, domain is all real numbers, right? But now we get down to the division, and now I've got a fraction here, right? 3x over x plus 5. And so we said what we have to watch out for is when the bottom equals 0. So in this case, I'm going to have a restriction on my domain, and the domain would be all real numbers, but x cannot equal negative 5. Remember, take the bottom, set it equal to 0, and that'll tell you what x cannot equal. So additionally, the domain of the quotient does not include x values for where the denominator equals 0. That's what's going right there. I don't know why the blank is split up in two parts. It's just where the number is not equal to 0. All right, let's do some of these and move on. All right, so here we're given a bunch of functions. I'm given function f, function g, function h, and function j, and I want to do some function operations. Okay, so half the battle, again, just make sure you pick the right function. On number 1, I want to do g of x plus h of x. So I need to make sure I grab the right functions. G of x is x minus 7, h of x is x squared minus 5x minus 14, and now I can just combine these. Once I plug in for g of x and h of x, again, my first step is to get rid of the parentheses by distributing the ones that are in front of these, technically. And then I'm going to want to group and combine like terms. Remember, you always want to start with your highest exponent first. So x squareds go first, and then I need my x's. So x minus 5x, and then I'm going to grab my constants, minus 7, minus 14. Again, make sure you show us what you're doing, your work nice, neat, and organized, but our final answer would be x squared minus 4x minus 21 when we have everything combined. I'm going to skip down a little bit. We're also going to look at the domain of the, as I state, the domain of the composite functions. So I'm also going to do that as we kind of go along here. In this case, in G, the domain is all real numbers. In H, the domain is all real numbers because, again, no fractions, no square roots. And then same in my answer, no fractions, no square roots. So the domain for this would be all real numbers. And it's basically that easy. That's all you're going to look for, square roots and fractions. All right, number 2 now we want to do f of x minus g of x. Again, make sure you grab the correct functions. So 4x squared minus g of x is x minus 7. And again, I think it's good habit, especially in the beginning. Put your functions in parentheses And there you go, remember things like on this one that I need to distribute that negative. Again, there's really a 1 in front of both of these. So 1 times 4x squared is 4x squared, but on the back I need to distribute that negative 1. And that'll give me negative x plus 7. And now good news for us, then I would combine like terms, but there are no like terms. This is already all in order, like terms combined, so we're good to go. That is my new composite function. Again, if I had to state the domain for this, look at the domains of your parent functions and your answer. So no square roots, no fractions, no square roots, no fractions, no square roots, no fractions. So the domain is all real numbers. So I'm sliding down to number 2 down below here, and all real numbers is the domain. All right, now let's look at number 3. On number 3, we want to do f of x times j of x. F of x in this case again is 4x squared, and j of x is 2x to the 1/2. And I want to multiply these together. When you multiply these, again, you're going to start with the coefficients. So 4 times 2 is 8. And when I multiply x squared times x to the 1/2, when you multiply bases, you add exponents. So 2 plus 1/2 is 2 over 1 plus 1/2. I got to get a common denominator, 4 over 2 plus 1/2, or I get 5/2. So this is 8x to the 5/2. No like terms to combine, so that's my answer. I would say I just need to now talk about the domain, and in this one again we got to be careful. You got to be thinking when we have this x to the 1/2, right? We talked last unit how that really means the square root of x, or when you have a 2 on the bottom again, that really means the square root of x. So if I've got a square root, that is going to restrict our domain, because in our domains we cannot have a negative number, because I cannot take the square root of a negative number. So my domain would be x is greater than or equal to 0. Okay, I can only have positive numbers. X can only be positive numbers for these functions. And again, it's being restricted because of that parent function j of x. All right, here we go, number 4. H of x over g of x. Again, I'm first going to grab my functions and just set it up. So this would be x squared minus 5x minus 14 over x minus 7. And now I need to try to simplify that, reduce that. And we said the best way, or the way we are going to reduce fractions, is by trying to factor. There's an easy trinomial, so things that multiply together to give me negative 14 and add together to give me negative 5 are negative 7 and 2. So this is going to factor to x minus 7 times x plus 2 over x minus 7. And now again, if I have the same thing on the top and the bottom, I can go ahead and kill. So my simplified answer would just equal x plus 2. But now when I talk about the domain of this function, I got to be careful because, again, we had a fraction here, right? Both parent functions, no square roots, no fractions, so we're okay there. But when I made my new fraction, when I made my new function, I created a fraction. And so, again, the bottom cannot equal 0. Again, going back to what we talked about before, when we kill off on the top and the bottom, that is creating a hole, but that is still an issue for our domain. So take that piece you killed off, or set that bottom equal to 0, and I'm going to get x equals 7. So my domain is going to be all real numbers, but x cannot equal 7 because it makes the bottom 0. So when I have a fraction, again, that's how it restricts my domain or affects my domain. All right. What I would like you to do now is go try 5, 6, 7, and 8 on your own. These are the same things, just same operations, just grabbing different functions. Go and work those out, and then also think about the domains of those functions, and then I'll have you check your answers. All right, here we go. Number 5, your answer is right here. Down below, it's x cubed minus 12x squared plus 21x plus 98. Again, no fractions, no square roots, so the domain is all real numbers. Number 6, your answer is 5x squared, and your domain is all real numbers. Number 7, when you simplify here, again, you do not want to move, you don't want to subtract exponents because that is going to put a square root on the bottom. So your simplified answer would be x to the 1/2 over 2x squared. You're just going to simplify coefficients, or root x over 2x squared. And my domain is x is greater than 0 because of the square root and because of the fraction. And then last but not least, here is number 18. distribute your negative